That's a challenge. All right. Hello, welcome. Do not read this slide. Just set of topics we're going to cover very soon. And we're going to talk about that stuff as well, but it's not going to be a part of the upcoming exam. And that's the question I want to ask in the beginning. So, you also should use the first question to check if your clicker correctly communicates with the computer. If you press the button and it blinks green, you're all set. However, if you press the button and it doesn't blink green, you may reset the channel. It's supposed to be 21. You should choose your answer. Remember, keep pressing. And I want to do this experiment live from Boston. It's Monday afternoon. All I want to do is just apply one force to one end of this plank and another force to another. Well, I could do it differently, for example, like this. Nothing. Or like this. That's what we could have called moving up the screen or down the screen. But of course, the question is different. The question is about what's going to happen if I apply forces opposite to each other, like this, but at different locations. So when I apply two forces like that, the net force is 0. And the velocity doesn't change. If initial velocity is 0, it remains to be equal to 0. And finally, that was very hard. Right. Well, how do we call this motion? There is a name. Rotational motion. That's a rotation. And the net force was equal to 0, but we observed some motion. Well, the right answer would have been, then answer number 1 is wrong, number 2 wrong, number 3 is wrong, number 5 is wrong. So what's left? Number 4. That's not a tricky question. That's just to start a conversation about rotational motion. Everybody knows how it looks like. Everybody knows the name. And rotational motion, from a kinematical point of view, from the point of view of the description of how it's happening, not much different from a regular circular motion. When we have an object like this board moving like this, so all individual point of this object makes exactly the same motion, travels along exactly the same trajectory. That's what we call it translational motion. And because all points are the same, we just look at one point. We can replace this plank with a dot and look at it. And normally, that dot represents the center of mass. We just look at the center of mass. However, in this situation, rotational motion, what is it? Well, each part of this board, of this plank, makes a circular motion. So just one makes a small circle, another one makes a large circle, but all those trajectories are circles, and the center of each circle is the same. That's what we call rotational motion. And of course, well, to describe it, we have to introduce some variables which should be handy, useful to analyze it. And of course, in physics, everything comes from experiments. So all you need is an object which can make rotational motion, like this one. So I want to fix this end. And now, if I apply a force, that's what it is. Rotational motion about this axis. And I can see what force is being applied by using a scale. Can I? Yes, I can. Not very good resolution. I need a new phone, I guess. In fact, okay. So I'm pulling on this. No. On this scale. Okay. Here. Now it starts making rotational motion. I'm making this rod move, and this rod makes move this heavy weight, 5 kilograms. And the force which I've been applying was about 20 newtons. But now, to make move the same exactly weight, I have to apply about 35 newtons. And the difference comes only from the new location of this scale. I've been applying the force here. Now I'm applying the force here. And that, you see, changes the situation. So the first conclusion is the distance matters. The location where the force is being applied matters. Now, another experiment. Same scale. I need eyes on my back. I don't see what you see. I have to use my imagination now. So I can attach a string because it's easier with a string to change the direction of the force. I can pull on the string like this. Okay. So still I have to fix this end. Okay. 90 degrees to this rod. And now I can pull on the string at a different angle and see if it makes any difference. Yes, it does. So now, to make the same weight move, I have to apply a different force. So two variables, in addition to the force, are important: the distance and the angle. And well, we can repeat many experiments like this, and we can arrive at a very convenient quantity, the new physical quantity which we want to use: torque. That's an official definition of torque. If we have a large solid object like this rod or that plank, it could be anything, it could be a wheel. And if we apply a force This arrow, this red arrow, represents the force applied to this object. That's, well, the point of application of this force. That's where this string is being attached. We can change the point of application. Yeah? We can shift it. And now the same force, well, the same string, force might be different, will be applied to a different location. So this is the point of the application of the force. And as we know, every force is a vector, and every vector can be resolved into two components. So now these two arrows represent two components of this force. One component points at the axis of rotation. That component has no name. Second, well, if we used our x and y axis, we could call it the x component of the force. But there is another component which is perpendicular to this line which connects the point of application of the force and the axis of rotation. That's a line. So this component we call perpendicular one. If this component is not 0, we take this number and we're multiplying by this distance from the axis of rotation to the point of application of the force. That's an official definition of the new physical quantity, torque. Do you use torque? Yes or no? Ever? Have you used torque in your life? Ever? Have you? Someone should say something. Yes?
Like this
when you're opening? When you're opening a jar, when you're using a wrench, when you're using a screwdriver, when you're opening a door, every time when you make something rotate, you're using torque. That's it. And it's a very simple experience. If you try to open the door and you push close to the edge, easy job. But if you try to open the door and by pushing close to the hinge, it's not so easy anymore. To make exactly the same effect, you have to apply much stronger force. Or we can say now, to apply the same torque, you have to apply stronger force because the distance decreases. And I also have a device. Well, you look like a strong person. So that's a torque feeler. You can feel the torque. So if you hold it, please, just keep this horizontal. What do you feel? Nothing. What now? What about now? Let's see. No? You should see his face. It's like, ah! You can't win. Nobody can. It's exactly the same force, 1 kilogram. But if you apply it a different distance, to compensate, you have to apply much stronger torque. Anybody, after the lecture can play with this for free today. Well, we can answer this question right now. That equation represents an official definition of torque. Those vertical bars, of course, mean magnitude. I'm not sure if I need it in the future. So R represents the distance from the point of the application of the force to the axis of rotation, and F subscript y represents the component of the force, of the applied force, which is perpendicular to the line connecting axis of rotation and the point of application. So, where's the question? Here's the question. So 10 people answered something already. This is the question. All right, don't worry. In case A, this is the case A. This is the case A. The magnitude of this force is 5 newtons. The distance from here, well, that's the length of the door, 0.9 of a meter. And you need to calculate the magnitude of the torque which is being applied in case A. And now, of course, you can choose the answer. So the magnitude of the torque equals maybe 0, maybe 4.5, maybe negative 4.5, maybe 1.5, 3.78. Neither of any numbers provided. Or you may have your own answer. For all your answers different from these, you can press 8 or 9 or 0. And actually, did you pass sign-in sheet? Okay, so there is sign-in sheet somewhere. Don't forget to sign in. And 5, 4, 3, 2, 1, 0, negative 1, negative 2. Okay. Now I tricked you. So next time, don't be tricked. By definition, the distance r has to be measured from the point of the application of the force to the axis of rotation. The axis of rotation, this term, describes any point of your choice. Like the origin. When you use a ruler to measure distances, you can choose the origin anywhere. So in many situations, there is physical action, axis of rotation, like a hinge. But it doesn't have to be always coincides with that mathematical point we use to measure distance. The axis of rotation is an abstract. That's a point which we choose. And we can choose it at the location of an actual physical axis, like a rod, a hinge, a nail. Or we can choose it anywhere else. And before we said clearly, specifically, which point represents your personal axis of rotation, you can't measure r. And if you can't measure r, you can't calculate torque. So in this situation, instead of pressing a button, you should have asked relative to which point, relative to what axis. And now, of course, we can say, okay, if I want to calculate torque relative to this axis, and usually we use either a capital O or a capital A. Relative to this axis, the magnitude of this torque indeed will be equal to 0.9 times 5, which is 4.5 newtons, right? However, if you've chosen a different location for that mathematical axis of rotation, mathematical axis of rotation can be chosen anywhere in the middle of the door, and that would change the torque. For relative to this axis, O prime, torque generated by the same force would be equal to 1/2 of 0.9 times 5 newtons. So that would be, well, 2.25 newtons. Newtons times a meter. Yeah, times a meter, sorry. There is no special name for the unit of torque. It's just a meter times a newton. And if I ask you, now, what will be the magnitude of the torque due to same force relative to this axis, O 2 primes? Same case, everything is the same, but the axis is here. Please choose your answer from the same set of the answers. This question is literally like this. You're pushing on the hinge. Kinda. Okay. From a physical point of view, if you had been at the hinge pushing like this, what would happen? So in my question, basically, from an abstract point of view, I'm doing exactly the same. This is my axis, and that's my force. And, okay, time ran out. 0, of course. Of course, we just have to apply the definition of the torque literally. So this distance r, as any distance, is relative. It depends on how we measure. And if we have to measure distance from the axis of rotation, which is here, to the point of application, which is again here, there is no distance. The fact that it doesn't exist mathematically described by this statement r equals 0. If you're multiplying by 0, you're getting 0. So a force is an absolute. It's wherever you read on the scale. But the torque depends on the choice of the axis of rotation. And when we say axis of rotation, we mean that abstract point we choose, which doesn't have to always be equal to the actual physical axis. All right. Now, every time when we talk about components, we arrive at a right angle triangle. And of course, in this situation, we also have a right angle triangle, which is formed by the actual force and by its components. So now we can use some geometry, right? This is my triangle, force triangle. This is theta, so this is theta. My actual force is the hypotenuse of that triangle. And the component which I use for the torque is opposite to this angle. So we can rewrite the expression for the torque. We can rewrite it. And this is the same distance from the axis of rotation to the point of the application of the force. But now this is the actual magnitude of this force. And this is the angle between two directions. One direction represents, this line has a name, line of action. So a straight line which is parallel to the force and which travels through the point of its application, line of action. Force acts along this line. And second line, second direction is that line connecting 2 points, the point of the application and the axis of rotation. So that's the angle. We can use it here to calculate the magnitude of the torque. So now we have two ways to calculate. Number one, using the official definition, using the component of the force which is perpendicular to this line. Number two, and number three, which you should be using in general. So now we are using a different geometry. If we extend the line of action, this blue line is the line of action. And then if we draw a perpendicular from the axis of rotation towards the line of action. And as we know from geometry, this kind of a line, the perpendicular, is always the shortest distance from a point to a line. So this segment, this shortest distance from the axis of rotation to the line of action has a name, the lever arm. And now the lever arm, this distance from the axis to the point of application, well, and one more segment, they now form a right angle triangle. So if we look at this triangle, this distance r represents a hypotenuse, and the lever arm is opposite to this angle. So opposite means use sine. Lever arm, L, is equal to hypotenuse times sine. So this product, r times sine, is equal to lever arm, L. So now we arrived at the third way to calculate the magnitude of the torque. Do this. I can't force you. I just strongly recommend. Normally, this last expression gives the fastest way to calculate. But it's up to you. You can try all three. It shouldn't matter in the end, of course. Now, this variable f, what does it represent now? Anyone? What did it represent? What did it stay for? The magnitude of the force being applied. Yes, exactly. That's the magnitude. I don't use vertical bars here. It's assumed. In this expression, this variable f represents the magnitude of that actual force being applied. And this letter L represents distance. Distance never negative. So, of course, that's how we calculate the magnitude of the torque. Again, the name for this variable is the lever arm of the force. The meaning is the shortest distance from the axis of rotation to the line of action, which means the angle between the lever arm and the line of action equals 90 degrees. This angle equals 90. It's a part of a definition. It's a part of a drawing. Now we can solve so many different problems. I have to remind you that when we talk about rotational motion, we use two agreements. Yeah, we don't. So normally, if we use two axes, x and y, x points to the right, y points up. But of course, in general, three axes are involved, x, y, and z. That's what we call Cartesian reference frame. So if I point x to the right and y upward, z automatically points at us. So we can't see it from this perspective. So we use terminology again. We call this direction out of the screen. And everything which is parallel to this direction is positive. Everything which is opposite to this direction is negative. And everything which measured counterclockwise from x, that's automatically is positive. And everything which measured clockwise, that direction we call away from us, we call it into the screen, and we call it negative. Torque, like angular velocity or angular acceleration, is either clockwise or counterclockwise. Well, if we look from above, if we use the top view. So here, relative to this axis, I have to set the axis first. So I choose my axis to be here. Relative to this axis, this force generates applied counterclockwise torque. We can imagine what should be happening to this door if nothing else is acting, only this force. It would start moving counterclockwise. So that's why we call this torque counterclockwise, or we should call it positive. So now, every torque, like every force or velocity or acceleration, has two features. First feature is magnitude. How do we calculate it? Well, we have three ways to calculate it. And second feature is direction or sign. Counterclockwise torque means it's positive relative to, well, our reference frame, but clockwise torque means it's negative. And if we have several forces acting, many forces acting, let's say here. Okay, still in session. Same rod, but now many forces acting on it. In this situation, at least two. There is a force from the scale, and there is another force, which is what? Gravity. The force of gravity, of course, acting on each individual part of this rod. So there's a little force here, little here, little here, little here, little here, etc., etc. And of course, all those forces acting on each individual part, we replace with one strong force, which applied to the center of mass. That's why center of mass is important. So for a uniform rod, the center of mass is right in the middle, so we have two forces acting on it. Well, we can call it tension, elastic force, because there is spring. And force of gravity right here, acting down, applied to the center of mass. Why is it important? Oh, because the point of application matters. This is the point of application of this force, and this is the point of application of the force of gravity. Why does it matter? Different point, different torque. And well, I can add some more forces like this, for example. Let's see if it actually, if it makes any difference. Does it? Does it change this? Changes, I know. I can't see, but I know. Because it's physics. So for this rod, free body diagram now should show how many forces? Nope. No? 4. Because this is also a force. See, this clamp is touching. There is a force, like a hinge. So 1, 2, 3, any gravity. 4 forces. So if we want to solve a problem related to this rod, we have to start from a free body diagram. So again, a blast from the past. We have to draw accurately free body diagrams. Well, this rod doesn't move. We call it equilibrium. So it's in equilibrium. What do we know about the equilibrium? Well, number one, net force is 0. So all forces point either up or down. If we add them up all together, positive and negative, has to be 0. But now we also must make an additional conclusion. Net torque has to be equal to 0. This force points up. What is the direction of the torque due to this force? No? No, it depending on what? Exactly. Do you know where did I assign? Did I tell you? No, I didn't. I said that's the clamp, but I didn't say that's the axis of rotation. Actually, in this situation, nothing is moving. There is no rotational motion at all. So saying axis of rotation doesn't really mean much from a physical point of view. But if we want to calculate or describe torque, we have to choose that abstract point we call axis of rotation. Where did I choose it? Thomas should say something. It's very heavy. I'm getting tired. So where did I choose it? Did I tell you? No. So if I ask you, what is the direction of this torque? What you should ask me? Where is the axis? So please ask me. Here. So now you can tell me, if this torque relative to this axis, positive or negative, or in and out, or clockwise or counterclockwise. And I agree, yeah. From your perspective, this relative to this point, that would be making something like that. That's what we call clockwise or negative. So this torque is negative relative to this axis. So now we have to consider all other torques relative to the same axis. So for example, this one counterclockwise, so positive gravity, same. This one, well, actually we don't know. In general, we have to solve for this force to figure out its direction. And then, well, in this case, it's probably up, yeah, because this is very heavy. Well, we'll see. We'll solve in the future a problem like that. So what's wrong with this choice? Nothing. But if we use this axis to analyze all torques, 1, 2, 3, 4, this one is hard to analyze because we have no information about this force. So what do? we choose the axis conveniently. We can choose it here, 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 but of course we can choose it here, because we can choose it where? Where? There's one word that answers that question. Where can we choose the axis? Anywhere. So if we choose it here, that force relative to this point has no torque. In this situation, only torque number 1, torque number 2, and torque number 3 matter, and one torque due to this force should be compensated by 2 torques due to those forces. Net torque has to be equal to 0. Now, we basically just need to solve more and more problems. Any questions? So for any problem related to an equilibrium of a solid object, we have to draw a free body diagram. We have to choose the axis of rotation. And we have to write, well, that was my example, kind of. And we have to write, well, at least one equation, normally more than one, if the problem is, well, not very easy. This equation, well, it's old-fashioned equilibrium equation for forces. Yeah. All forces must cancel each other out. We call it force balance equation. But now, for a solid object, for the object which is big, has size, and might rotate, we should add the second equation. We should set the net torque to 0. And what is the net torque? The sum of torque number 1 due to force number 1 plus torque number 2 due to the force number 2 plus torque number 3, etc., etc. Some of these are positive, some of those are negative. And that equation we call torque balance equation. We can write it in 3 different manners, 3 different ways. The top one, that's literally what net torque is equal to, the sum of all individual torques. So the top equation assumes that each variable, how do we call it? Anyone? That's a Greek letter. We know mu, we know nu, and this is tau. Yep. And this equation assumes that each variable represents an actual value which is magnitude and a sign, plus or minus. But we can rewrite it differently, like this. We can explicitly show pluses and minuses. So each counterclockwise torque is positive, each clockwise torque is negative. So if we write it like this, the same variable now means a magnitude. Or we can write it like this. The sum of magnitudes of positive torques should be equal to the sum of magnitudes of negative torques. Balance. Whichever you want to use, it's up to you. This is probably I use most often. Now, let's actually do a problem. This is the invention of balances. That's how people used to measure weights. for thousands of years, maybe even more. Well, this balance is broken. But I can fix it. All I need to do is just find the point of the application of this force. How many forces acting on this meter stick right now? How many? Yes. The pivot of hinge, number 1, number 2, and there's a force of gravity applied to the middle of this meter stick, number 3. So the net force, of course, equals 0, but now we also can add the torque balance equation. The net torque equals 0, and all we have to do is just draw a free body diagram. So force, force, force. That's the first step. Free body diagram. The second step, what is the second step? Axis. Where do you want it? We have 3 natural points. You can choose anywhere, but natural locations usually is one of the points of the application, So this is the point number 1, that's point number 2, that's point number 3. You tell me which point do you want to choose. Democracy wins, so the majority. Of course, I could have it overruled, but I won't. And while waiting, I want to show you another situation. Well, they should have been, well, they're actually pretty close to 0, yeah. So now, each scale shows you a force, and the board is in equilibrium. It's practically horizontal. So right now there's force number 1, force number 2, and force of gravity, 3 forces acting on it. And depending on, well, the positioning, the readings are different. But I also can add a weight. I can add it like here, for example. And you can see that also changes the readings. And we can calculate each reading by applying the torque balance equation. But what's interesting going to be happening to this reading, if I start moving this weight, eventually, see, there is that critical point when this board, well, the board exerts the normal applied force and the normal force exerting back. And the normal force is the force acting from this wedge on this board. That's what we read. Eventually, there is that critical point when the normal force equals 0. If we move it even further, it topples. For example, if you have a scaffolding and you walk, should be careful, because it might be a critical point when you might actually fall off it. How can we calculate this critical point? Well, this force has to be equal to 0, and well, And the net torque also has to be equal to 0. Any questions? All right, thank you. You're ready. You're ready for your near future, which is a lab, and almost ready for your far future, which is an exam. And these are your answers.
Sure, I didn't snap the attendance sheet.
Attendance sheet. Please wave the attendance sheet. Yes.
For the practice problems on WebAssign, do you have to create those, or is there some way that I can get them for practice? I know you said you weren't going to give them out because it wasn't really utilized.
Yeah. So
It was very helpful for me for lessons.
those problems are taken from the textbook. It probably just
So just use the text.
easier, yeah, just to use end of the chapter problems. You can print out like 3 or 4 pages.
Is there because like the good thing about WebAssign is you know the answer.
I know.
So like if I do all the problems, I don't know if I got them right.
Well, I know. I would recommend collaborate with people. You know, like I'm doing this problem, page this, page that. That's my answer. What do you want to do? Do you agree?
You don't have like some answers to the book?
No, I don't, unfortunately.
All right. All right, thank you.
I got this email, but I'm not one of the ones that's not registered.
Your number might be different from the actual number it uses. So now I know your number. But what I want you to do is send me an email and just take a picture of this and send it to me.
Okay.
And I'm still going to I'm the person registering you, so I will register you.
Again, also take a picture of this part and email it to me.
Okay. Did you say today we need to email the answer for the last question?
Last question about what?
The last question about the.
No.
No, we don't need to email.
No.
Okay.
it's
The only person I decided to, yeah, think about it every day.
25 grams, $1,500. Sometimes the food imports from China have this stuff. Right, and so they make it out of, they make this oil here in this semester. Yeah, oh, yeah. They make this oil here in this semester. They kept it. They have them hydrolyze this off. Wow, so you have a lot of stuff.
Yes, I do.